Cool. So my name is Chris Lang, and I'm a PhD student in the EECS department in MTL, which is the Microsystems Technology Lab. And today I'm going to talk about one-class fault detection for manufacturing settings using Parzen window classifiers. So just give a quick overview. I'm first going to start by recapping the problem itself. So last week, Jack Dillon, who is an equipment engineering manager at ADI, sort of gave a run through of some faults that he had seen in at ADI. And so just quickly run through those again and also give a recap of the general problem. After that, I'm going to talk about some of the guiding principles and assumptions that went into deciding a solution to this problem. Then I'm briefly going to touch on some of the other possible solutions which I think could have worked as additional solutions to this problem. And then after that, I'm sort of going to get into the meat of the presentation, which is talking about the Parzen window classifier and how it can be applied to detecting faults in manufacturing settings. So I'll talk about a few of the design choices behind it, such as the choice of the kernel, the way that we end up training it, and how we can adjust the model to deal with concept drift. After that, I'll show some of the actual results on the two sets of faulty data that we have. The first is ion implantation, which we were talking a little bit about before, and the second is plasma etch. Then at the end, I'll talk about a few improvements which I'm still sort of working on and things which I would like to incorporate into the model. And this is mostly future work. So just to give a general overview of the problem itself, it's a very general problem. What we really want to do is just detect faults or anomalies in general manufacturing processes, although specifically I'm looking at semiconductor manufacturing processes. And in particular, the data sets that I was looking at came from two different sources. They were a plasma etch data set and an ion implantation data set, which we sort of briefly just covered what those were. So this is an example of a fault from the the ion implantation process, where this x-axis is time. And then these two curves are really the two most important sensors. They're the wafer position, which is the position of the wafer on that big wheel that we were showing before, and then the measured current. And generally, these the measured current should be a function of the wafer position. So when the wafer position is high, we tend to get a high measured current, and it sort of follows this particular pattern here. But at some point in the processing, there was a fault in the machine, and we did not see this characteristic pattern. And this is really what we want to detect. So if we can detect this early on, then we can not continue processing all of these wafers. We can fix the machine before we process additional faulty wafers. And possibly even if we can detect it very early on, we can do predictive maintenance on it. So in general, the data that we're looking at consists of multi-sensor time series data. So you can imagine that we have many different sensors, in this case, S1 through 5, that at each point in time have some value. And I like to think of each data point or each point in time as a single point in this multi-dimensional space, where each axis here is the value of one of the sensors. And as this process is moving along in time, it tends to trace some sort of trajectory or a path through this multi-dimensional space. And that just sort of, I think, is a nice way of visualizing what's happening. So there are two.
And I think just one point for those of you who weren't on last time. As you know, a semiconductor is made up of many layers. And in this case, it can be up to 3 months between when you actually have a faulty process like this, you're actually able to identify it in electrical test. And it's only through electrical tests that they can identify this problem, because there's 100 and some layers. So obviously they've got a lot of labor and effort and time that's been put into that part, only to realize that it's bad. So if they can determine immediately that it's bad, then they save 3 months worth of inventory and processing time. Mm-hmm. And there's no other way other than doing this for them to determine that. So that's the relative importance of this particular problem. And it's usually millions of dollars, or certainly hundreds of thousands of dollars worth of scrap when this happens.
Yeah, so not only do additional processing on the wafer itself, which is sort of a more minor point, But if it takes 3 months to get to the end of the cycle, then, and you haven't detected or fixed the fault by then you're losing 3 months worth of product in that time period. So detecting it as soon as the fault happens is really the critical part. So sort of with the general problem setup in mind, there are two big assumptions which I was making. The first and most important is that we really only have access to known good data. And this is because we won't necessarily have examples of the fault before it happens, and we won't even know what type of fault there is. There can be probably an infinite number of different types of faults, and really all that we have access to is known good data. Additionally, we'll probably never end up seeing the same fault twice, so we cannot rely on having sort of multi-class data where we have both examples of nominal data and faulty data. So with this in mind, there were sort of two different principles which I was thinking about in order to come up with this classifier. The first is that we want to keep it as general as possible. And this sort of ties into the idea of the 80-20 rule, where we want to create a general fault detection algorithm that captures the majority of the faults. So we get 80% of the reward without needing to design this algorithm for a specific process or for a specific fault. This is about 20% of the possible work. We don't want to design it for each individual process and each individual fault, because that would just be way too much work. So what we end up doing is something called one-class classification, where instead of in traditional multi-class classification, where you try to separate two different classes of data, what we try to do is just try to draw the tightest boundary that we can around known good data. So if this is the data in this multidimensional space, we just want to draw this boundary around what's known good. And if a new incoming point falls within this boundary, we classify it as good. And if it falls outside, then we classify it as bad. So I guess before diving into the solutions which I ended up looking at, I was curious if anyone else had anything that came to mind, any sort of general method which you could.
Can you describe which, in this case, what sensor 1 and sensor 2 are?
So they could be something like the temperature. This is just a generic plot, but it could be something like the temperature of the chamber. It could be the pressure, like things like temperature, pressure. In the ion implantation case, it was the beam current and the wafer position. But it could really be any sensors that are measuring the health of the process.
So some sort of autoencoder comes to mind, or like any sort of process that like estimates like a generative, any sort of generative model, basically anything that's like generating a distribution of your good data.
Yeah,
seems like a place to start.
That,
which I think is basically what you're doing.
Yeah, that is essentially what all of the possible solutions boil down to.
Yeah. So like an autoencoder, I guess, would be one option.
Yeah, and so I think in 2 weeks, Damien is working on an autoencoder-based solution where essentially he takes all the examples of known good data, he puts it into an autoencoder, and then he creates, I think it's a Gaussian mixture model on those encoded features. So it's sort of a lower dimensional representation of what's going on. And then if new incoming points sort of fall within those distributions, then he classifies them as good. Otherwise, he classifies them as bad. But yeah, in general, I think that you're right. Sort of a generative solution where you have some estimation of the likelihood of it coming from the same distribution as the known good data is really what all the possible solutions boil down to.
Yeah, so I guess this is something that I'm like starting to work on a very similar problem where I have like a multi-dimensional time series and like severe class imbalance and quantity fault detection. And one of the things I'm starting to think about is like how do you evaluate, or how did you evaluate these like different generative options? Like how do you think about the pros and cons of these different generative options?
I'm glad that you asked that.
Okay.
There's with some past work on these specific problems, both from on this particular problem, both from ADI, which is the company where Jack works, who presented last week. And in their case, they used sort of a traditional convolutional neural net classification approach. But this assumes examples of both known good and bad data. And they were really just designing the fault detector for this one known fault, which was very common. There were also previous students in Dwayne's group who tried to create an LSTM approach, which tried to essentially predict future sensor values based on their current ones and compare that to incoming data. But it's sort of a little bit strange in my mind because it essentially just created, it would oftentimes just output the same sort of nominal signal, and it wouldn't depend. And it was basically just a comparison between the sensor values and some reference cycle is basically what it boiled down to. But I think that sort of the more interesting class of approaches are these true one-class classifiers. And there are a few different ones, which I was going to talk about first before going into the Parzen window classifier. So the first one is one-class SVM, which is sort of an extension of the traditional multi-class SVM approach. The second is one-class GP, or Gaussian process model. And then the last one is a GAN-based or generative adversarial network-based classifier. And I think this one in particular is pretty interesting. So I was just briefly going to cover these three and then finally talk about this Parzen window classifier, which is what I ended up using.
So can I ask you a quick question before you do that? This is more basic, but are the is the length of your time series the same for each observation or not?
No, not necessarily.
Okay.
So it depends. So I think for the ADI approach, they ended up just cropping it so that it was always the same.
Okay.
But I don't necessarily think that you should make that assumption.
Okay.
Because if there's just an additional data point in the run or the cycle, you don't want that to completely, maybe there's important information there. You could probably do some post-processing to squeeze it all into the same number of data points. But I think in general, it makes sense to not design it such that you assume the same length.
So how have you designed your solution? Have you have taken their assumption that it is the same length or no?
No, I did not.
Okay.
I basically look at each point in time and also perhaps some additional points around it as sort of individual points that I'm classifying. And then if a single point in the run flags as faulty, then I classify the entire run as faulty.
Got it. Okay. Sounds good.
Cool. So one-class SVMs are sort of an extension of the traditional support vector machines. And just to give a brief recap of these, support vector machines try to create a hyperplane, which creates the largest margin between two different classes. And really the core of this is what's known as the kernel trick, which allows you to project some features in your original feature space into, so for example, our sensor values into a higher dimensional space. And when you end up doing this, you can end up getting an actual linear separation between the two classes. So just to give another visualization of this, if this is your original data and you have two variables, sensor one and sensor two, there's no good linear boundary between these 2 points. But then when you apply a kernel function to this in this higher dimensional space, you can more easily separate the two of them. So you can create this nonlinear classification boundary between them. So this is for the multi-class case when you have both good and bad examples. But in the one-class case, you have to change this a little bit. There's actually two different ways of approaching the one-class case, but they all give you actually the same solution when you use the same kernel function, or when you use the common Gaussian kernel function. So the first is to basically draw a circle around, or the tightest circle that you can around all of these points in the projected feature space. And the second one is to try to separate these projected features from the origin. So the pros of this are that it tends to scale pretty well with the data size, because really what determines this classification boundary are just a few number of support vectors. So in this, which are the points which sort of determine this classification boundary. Here it's the points on the margins themselves. So this 1, 2, 3 points are really the support vectors. And when you're doing the classification, you can actually ignore all the other points. So it tends to actually scale fairly well with large data sizes, and it can give pretty accurate and interpretable classification boundaries. The main con, which I have run into, is that it's sort of non-trivial to train these hyperparameters when you only have known good data, which sort of ties into the way that the cost function is written. And also, it can be costly to do the initial retraining, even though doing predictions may be computationally quick. Doing the retraining can actually be pretty costly. So the second method which I was looking at was one-class Gaussian process models, or GP models. And GP models are typically used for regression, and I think that they do a really good job at small data problems. So this is a regression example here where we have some input x, and we want to be able to create a model for f of x. And we only have just a few training data points. What it does is it tries to correlate this query point that we want a distribution for to all our past observations. So if we are choosing a query point very close to one of our past observations, it can create a very tight distribution because it's very heavily correlated to one of these. But then as you get farther out, it will give you still a nice interpolation between the points, but a larger confidence interval. So you can actually easily adapt this to classification problems, either multi or one class classification problems pretty easily. So if you only have known good data, what you can end up doing is using the positive label 1 as the output f of x that you associate with these known good features. And you end up using a zero mean Gaussian process model. And then if a new point falls below some threshold, you label it bad, otherwise you label it good. So you can imagine here, these red x's could be points where you have examples of known good data. This blue line is the Gaussian process regression function. And then you can draw a threshold here and basically says, if your prediction falls above this, so if it's close to these points, you'll classify it as good. If it falls below this in one of these areas, classify it as bad. The pro of this is that it's nice because it gives you a probabilistic output. So not only will it say how good or bad something is, but it can tell you how confident you are in that. It also tends to consider many points, or sort of the weighting of them, to determine this underlying function, and not just a few key support factors like an SVM. But really the main con of this is it tends to scale poorly with data size, and it can be pretty computationally intensive. So for that reason, I think that this is really best used when you only have small numbers of training points. So the last method, which I was going to talk about real quickly, was GAN-based classifiers. And so these are based on neural networks as opposed to the non-neural network approaches, which I was talking about before. And Fan Keng in the audience here is actually the one who brought this to my attention. So GANs are typically used to simulate data from some sample distribution, and they are comprised of two different parts. There's a generator and a discriminator. And the generator tries to take in noise and spit out synthetic data, which matches data from a real-time series. Then the discriminator tries to determine if the data coming in is either real or synthetic, and then outputs its predictive label to feed back into the generator. And so then you can use this to sort of adversarial train both of these in order to trick each other. So the discriminator is trying its best to determine if it's real or synthetic, and the generator is trying to create the best synthetic data as possible. Normally, what these GANs end up used for is just taking the generator and using this to create examples of data from this known distribution. But actually here, what I think makes a lot of sense is to be able to use this discriminator in order to determine if some new data coming in came from the same distribution as this real nominal time series data. So I think that the pro of this solution is that it's really the most true big data solution here, where all the other ones will scale with the amount of training data that you have. So because the neural net is a fixed size, it can scale very well with large amounts of data. And it can also learn the most complex signals. The cons of this is that it can actually be practically very difficult to train, especially this adversarial training here. And you also need lots of data enabled in order to train them effectively. So the method that I ended up settling on was this Parzen window classifier. And Parzen window classifier is essentially a density estimation technique. And in many ways, it's sort of the simplest of the four. So it like SVMs, it relies on a kernel function, which you essentially stamp onto these training data points in order to create some density distribution to evaluate the testing points. So in a multi-class classifier with both labeled good and labeled bad data, you can create density distributions for class 1 and class 2, and then you can look at the difference of the two of these to see which one is more likely. So if you have some new point that comes in that falls in this yellow area, you would say it's part of class 1, and if it falls into this blue area, you can say that it's class 2. And then in the green, you'd say somewhere in between. But again, we can end up using this for the one class case where we only have example of known good data and no faults, where again, we'd create a distribution for what we think the known good data should look like. And then if a new point comes in that has some density less than a threshold, we'd classify it as faulty. So if it falls out here, we would classify it as faulty. Otherwise, we'd assume that it's good. So one of the most important parts of this is actually the choice of the kernel, which we end up creating this distribution with. And the most common kernel that people typically end up using is the Gaussian kernel, sort of similar to the SVM. But this is actually pretty problematic when you have imbalance, which can be common in manufacturing cycles. So you can end up having manufacturing cycles which have sort of infrequent points in them, but we don't want to classify as anomalous. So this is sort of one of the sensors from the plasma etch process as a function of time. And then this is the likelihood of the points as a function of time again. And we can see that at these transition areas, it thinks that they are very uncommon because the density of points at this edge, when you have large amounts of data, is actually very low. So if you only have a very few number of points at these edges here, you would end up raising sort of faults or anomalies at those points because you think that they are unlikely. So instead, what I ended up using was a binary kernel, which is basically just says if you're within some distance of it, give it a 1. If not, give it a 0. And using a threshold of 0 of this to make sure that we don't raise faults on any uncommon parts of the cycle. So basically, if it is within some distance from some known data points, then we can say that it is known good. And if it's far away, then we would just say that it's bad. So this is pretty equivalent to, this is equivalent to what I would call sort of a minimum distance classifier, or just using the distance of incoming points to all past data points as our classification metric.
So of course, do you mind if I ask again about this? I'm kind of fixated on this, like the length of the time series and whether it's the same across everything. So just to make sure I understand what you're doing, it looks like you're comparing. So you have a data point at t = 1 across all of your observations, and are you basically building a distribution for all of the values at t = 1 and t = 2 and then t?
It's one distribution across all time, okay. Points in all time.
Okay. So then why, this might be dumb, but why are you not getting one likelihood for the whole time series? Why are you getting a stream of? Why are you getting a likelihood that's changing over time?
Because each one of these points can be compared to all. What we're doing is we're comparing one of these points in time to all past points that we've seen in the past. So that's sort of the answer to your first question. And then we do that for each point in the cycle.
I see. Okay. But what about points that, like values that could be common at certain points in time, but may not be common at other points in time?
Yeah. So what I almost always end up doing is using time as an additional sensor.
Okay.
And so then if you end up having, which I haven't talked about this yet, but a very tight length scale for the kernel, for the time dimension, it will in effect only look at points at similar times.
I see. Okay.
So even if you have some small amount of jitter in the signal, there'll be a small window around that. So it doesn't have to be perfectly exactly at the same time, but it will still end up looking or positively, however you want to define it, classifying these points as good, even if there's a small amount of jitter.
Okay. Yeah, that makes sense. Interesting. Okay. Did you consider other approaches for time, dealing with time?
Yeah, so this is something else which I'm still working on and I didn't really put in this presentation, but I do think that it would be a good thing to, I haven't really thought this through yet, but some way to still incorporate the Gaussian kernel, which can give less, it can sort of give smoother classification boundaries, but still having it deal with this sort of infrequent part of the cycle problem. So what I really would like to do is only consider these points in time for the underlying distribution, and then perhaps use the Gaussian kernel for that. But it was not immediately obvious to me how that could be done.
Mm. Mm. Yeah, I mean, another technique that I've come across is dynamic time warping.
Yeah.
Have you considered that at all?
Yeah, so that was something that one of the previous students, I didn't mention it, but there was actually a group of 3 students who ended up working on this problem before, and that was one of the ones that they ended up looking at. I think that the problem with that, I don't 100% remember, but I think that the problem with that is that it was just not computationally fast enough to be able to do on the fly.
I see.
But I am not 100% certain on that.
Okay, all right, interesting. Thanks.
Yeah. But I do think that, yeah, that is something which I would like to look into.
Thanks.
So sort of just to demonstrate why this infrequent or uncommon part of the cycle can be problematic, I made this really simple toy problem where you can imagine 2 different parts of a manufacturing cycle where you sort of have the core of the cycle, which are these points in this loop here, and then maybe some startup or some ending part of the cycle where the sensor values are out here. And if you end up using this Gaussian kernel, a point in the center of this loop, which would be a true anomaly, would seem more unlikely than a point that is at this infrequent point, perhaps from the startup part of the cycle or ending part of the cycle. So you would either need to choose the threshold such that these infrequent points out here are flagged as anomalous, or you would have to raise the threshold so much that you would start missing anomalies which could occur in the center here if you end up using the Gaussian kernel. But if you use this binary kernel instead, then you could get sort of this minimum distance classification boundary where it would just draw sort of an outline around what you would expect these traces to be. So this is sort of the approach, or this is the choice of kernel that I ended up using just because it is so common to see very sort of uncommon parts of a manufacturing cycle for specific sensors that we don't want to flag as anomalous, but will happen every run. So I've sort of talked a little bit about the model itself, but I haven't talked about how you end up training the model. And training the model is essentially comes down to selecting the kernel length scales for each of the sensors. So the length scales are basically the scaling of the sensor dimensions that are used in the kernel. And this basically says A, how important is each sensor, and B, how much space is considered nominal. So in general, increasing the length scale tends to expand and smooth the classification boundary. So this is just examples of classification boundaries for 2 different choices of length scale. The first is an even choice of length scale where sensor 1 is as important as sensor 2. And then this is one where sensor 1, the x-axis, is considered less important. So you would choose longer length scales, and you could have sort of a larger range there than sensor 2, the y-axis. So normally the way that this would be done, if you have examples of both good and bad data in the multi-class training approach, is to choose length scales such that they reduce your validation error. And this is just a simple illustration of how this could be done. So here the blue are considered known good points, and the red are considered good points, and the red are considered bad. The filled ones are your training points, and the hollow ones are your validation ones. If you have examples of both, what you would want to do is choose these length scales in order to minimize your validation error or the classification of these hollow points. So sort of the intelligent way would be to choose these oval-shaped horizontal length scales such that you correctly classify the red and the blue ones, the hollow ones. And then an example of this not minimizing the validation error would be if you choose these vertical ones instead. So then here, all the hollow points are misclassified. But we don't have the luxury of having examples of both good and bad data in order to train our model on. So what we need to do is train our model only with known good data. So this is, I ended up choosing this one class cross-validation training technique where what we want to do is create the tightest boundary possible. So practically what this means is minimizing the sum of the length scales. So choose the tightest boundary possible such that when you do cross-validation, none of these good points are misclassified. So essentially, we just rotate through all of the known good points, pull them out of the training set, train on the other ones, and then make sure that the new points are still correctly classified. So I ended up doing this on the ion implantation data, and the initial results were actually fairly heavily influenced by concept drift. And concept drift is common in a lot of different manufacturing settings or just systems in general, where the underlying conditions tend to change over time. So the initial results that I ended up using used a fixed data set from the very beginning of the process, so maybe like -100 to 0 here. And it probably worked well for the first 100 or so, or 100 to 500 cases. But then as this system was changing over time, you could see these both sharp drops, for example, right here, where maybe some maintenance happened, or some drift over time, where maybe the chamber was wearing out, or in some way the system was slowly drifting. So when we ended up comparing these new points to very old data, it was much more likely to raise false positives. So what I ended up doing was using this sort of floating model idea, where after you initialize a model, you can adjust the data set in order to adapt to the changing system. So it's pretty simple. What you end up doing is when a new point comes in, if it is within this classification boundary, you can add it to the known good point, and likely remove the oldest point just in order to keep that sort of data size from blowing up. And also, if it is not within this classification boundary, you raise alert and you don't add it to the known good set. So this had sort of the effect which I was hoping to see, which was when we do use the floating data set, it gets rid of a lot of these sharp drifts or sharp changes and drifts over time. So instead of seeing these sharp drifts here and or sharp drops here and drifts over time, we see a much more constant sort of baseline anomaly score with only a few distinct anomalies, which are really the true anomalous events that we want to detect. And so I think that this helps adapt to concept drift, but we could also use it. We could also sort of look at this to detect if there is long-term drift happening in a system, which we may want to be aware of, for example, for predictive maintenance. So the idea here is that you could have two models. One is a floating model, which sort of uses which I was talking about before, where you're changing the data set in order to adapt to the changing conditions. And this could detect sort of sudden changes or discrete faults in a process. And then you could also have a fixed model, which can be used to determine the total amount of drift since the model's creation. So for example, since you started doing maintenance. So if you were to sort of think about what would happen over time using both of these models, if you look at the anomaly score, the floating model would sort of stay at a constant amount, except when a discrete fault would happen, and then this would trigger a fault alert. If you also have this fixed model from the beginning of time, as the system is drifting, this anomaly score will be growing over time as well. And then when it crosses some larger threshold, you would want to trigger a drift alert for that. And so this way you could both be able to detect discrete events like true faults and also determine when the model has drifted too much. So sort of with this concept drift idea in place, I apply the model to the two data sets that I saw, the plasma etch and the ion implantation data set. For the plasma etch data set, I ended up training it using about 200 known good runs. And there were about 5 sensors in this process, although about 2 of them really contained the majority of the faulty info, and the other 3 were sort of uninformative. So there were sort of 2 different types of faults. All of the faults had sensor 2 drop down sort of at this location. So this sort of top distribution up here is the nominal sensor, what it would look like. And then sort of this group here is what a fault would look like. Additionally, some of the faults also had this other sensor, sensor 5, have very obvious anomalies in it. So all of these faults were actually linearly separable if you knew what you were looking for. So for example, just the value at this one point in time. But some of the faults that didn't have this sort of large jump in sensor 5 may have been more difficult to detect because these two traces, you may not always see this large example here. You may only get this type of signal for sensor 2. So applying the model, I got a false positive rate of about 17 out of 1,400 cases, which is about a 1.2 false positive percent, and a false negative rate of 0 out of 480. So we raised alerts in about 1.2% of the cases when we shouldn't have, but we were able to catch 100% of the faults that did happen. And if you end up looking at the sort of distance to the training set, which is sort of equivalent to the density that I was talking about before, you can see that there are definitely two discrete types of faults. So this area here is sort of the more subtle types of fault that does not include this big jump here. And then everything else here, which includes beyond 3, includes all of these cases. So what's actually sort of interesting is if I chose the threshold differently, slightly higher, you could have perfectly separated these and gotten 0% false positive and 0% false negative. But because by definition of the model, we ended up a priori choosing the threshold as 1 and then choosing the length scales around that. Our threshold was chosen before during the testing. So that is why even though they're linearly separable here, we still do get a small false positive rate. The second set of data that I was looking at was the ion implantation data. And so in some way, this was a little easier because there were actually only 2 important sensors that we were looking at. But in some way, it was more difficult because the faults were not as easily separable. And there were also a large number of borderline cases in the data, which may have been difficult to classify and also could have snuck into the training set in that concept drift idea and affected the results that way. So the beam current is really the most important sensor. And this is an example of what it looks like nominally. This is an example of the fault, in particular this point here, where the beam current drops to 0 in this valley. Except there were also a lot of borderline cases where it didn't fully touch 0, but it sort of came close. And talking to the process engineers, they said, this isn't good, but it's not going to kill a run in the same way that this would, or a very severe fault like this one will. So they wouldn't really classify it as a true fault. And there were, what made this more difficult is really the large number of these borderline cases, which really are good, but are very similar to the faulty cases, or some of the faulty cases, I should say.
I think the interesting thing is that if you have a significant number of these borderline cases in a row, or at least within a run, then that will create a fault.
Yes.
That's a little bit out of scope for, what we're trying to do right now, but it's kind of another dimension that, well, okay, then how would you sum up, all of those faults over time and determine that if you have they're not faults, if you have so many borderline cases, then that actually will create a fault.
So I think that also sort of ties into that fixed and floating model idea, where if we were to use the fixed model, we would see in areas like this, that this is probably an area, if I had to guess, where there's a large number of borderline cases. And if you sort of look at this plot, and I would also say put maybe a low pass filter on so it's more interpretable, I would expect to see this average value raising over time here. And then if you have a second threshold, maybe on that smoothed out version of the curve, then you would be able to detect a long-term drift or a large number of those borderline cases. So the ion implantation results were pretty similar to the plasma etch results. But sort of what was interesting here is that I noticed the misclassification rates tended to depend a lot on the training size. And really, I think this makes sense because the more training points that you have that you're comparing to, it sort of tends to expand that nominal area. So increasing the amount of training points tended to raise the false negative rates. So we're more likely to say that a fault is nominal, and it decreases the false positive rates because we end up filling in those areas which we may have not seen beforehand. So in general, the false positive rates were around 0.1 to 0.5%, which is pretty good. But the false negative rate was, oh, this should say 20%, was about 20%. So there were about 11,000 true negatives, and we misclassified at most maybe 50 of those, and there were about 50 true positives, and at most we classified about 10 of those. So you may say that you want a smaller, you may say that you want a smaller false negative rate and a larger false positive rate. And one way that you could do this would be to raise the threshold that you set for misclassification. And so in the multi-class case, this is pretty easy because you can choose your threshold based on the ROC curve. But we actually don't have access to this a priori, so we wouldn't know what these rates are when we create the actual model itself because we haven't seen the faults. We haven't seen the faults yet. So instead, what we could only choose would be an acceptable false positive rate and then choose the length scales based on that. Because we don't know, oh, this should say false negative. Because we don't know the actual false negatives, or sorry, false positives, we can't use that to inform our decision of where the threshold should be. So what we can do is choose an acceptable false positive rate and then choose the threshold based on that. So in practice, what this would mean would be choosing a different set of length scales for the model. So in the cross-validation, if we have some acceptable false positive rate in the training, what we would say is we could relax these constraints to allow some percentage of the cross-validation points to fall outside of the boundary. So when we end up doing this cross-validation, which tries to choose the tightest set of boundaries, we could allow some of these points, maybe 0.1%, to fall outside of its boundary. So I ended up doing this on the ion implantation case, and it had sort of the results that we would expect. As you increase the acceptable false positive rate in the training set, it increases the false positive rate in the testing set as well. And it also ends up decreasing the false negative rate. So I think it went from about something like 20% to something like 95, or to something like 5% false negative rate. And sort of what was a little bit interesting is that the actual true false positive rate was lower than what we expected based on the acceptable false positive rate. And so without going too deep into this, I think that that sort of suggests that there were a lot of these borderline faults in the training set, which we really shouldn't have been using to evaluate the likelihood of new incoming points. So just to talk a little bit about some of the changes to this model, which I would like to look at. The first is multi-recipe modeling. So being able to look at many different similar related processes or recipes using the same model. Also ways to improve the robustness of the model. And finally, one of the downsides of this is that you can require a lot of training data as the number of sensors increases. So what I call the semi-correlated approach could be a way to deal with that. So like I was talking about before, the previous results were really only from a single recipe or maybe a procedure of the tool. But one tool can have many different recipes or many different procedures that it's trying to run. And we may just want to build a single model that could correctly classify all of these different recipes. And the question is, how do we incorporate different types of data from different recipes? So just a really simple illustration of how this can be problematic. Let's say that we have two different recipes, recipe 1 and recipe 2. And the blue line here is sort of the nominal trajectory, and the red line would be the faulty trajectory, or an example of a faulty trajectory. If we put all of the data into the same data set, when we see something like 2 or 3, it's going to compare 2 to 4 and 3 to 1 and say that it should look nominal. So that's something that we sort of want to avoid. A few different ways that we could deal with this. The first is what I would call length scale transfer learning. So really the costly part of the training is the choice of the length scales. And we could still very easily have one model per recipe, but train all of these length scales over all of the data sets. So we could have individual models for each recipe, but one single choice of length scale, which has been trained over all of those models. A second approach could be to normalize the data. So oftentimes these recipes or procedures sort of tend to be grouped into different families, which will only differ by something like time or intensity of the process. And oftentimes you could end up just normalizing the data to model all of it jointly. And actually did end up doing that for the ion implantation process. And that worked really well in that case. A third approach, which I'll just mention briefly, I would call sort of process parameter modeling, where we could end up appending process parameters or sort of the parameters of the specific recipes or feature or procedures as additional features that we end up putting into the model. And so this would have the effect of adding separation between these points in the process space. So if we end up having another access, which for example, in this case, could be a process parameter that differs between recipe 1 and 2, now when you compare recipe or this point 1 and 3 here, if you don't have this process parameter as an additional feature, they'll look the same. But if you add this as an additional feature, you'll add separation between these 2 points. And when you see this point 3, it will not say that it's similar to point 1, because even though they're the same in their sensor values, they differ in their process parameters. So you will not end up incorrectly classifying this fault. Another really important point about this, which is something which I'm currently working on, is robustness. So I think a big downside of this is that the current approach is pretty sensitive to the training set. And if you end up just having a single outlier in the training set, so if a fault just happens to sneak in, it can easily prevent detection. And having an acceptable false positive rate helps, but oftentimes it's not sufficient. So one approach which I think makes a lot of sense is to actually change this classifier threshold from 0 to k-1 over n, where n is the total number of points. And essentially what this means is that instead of requiring 1 point within some distance, you require k points within that distance. But really, the problem with this that I'm still working on is the best way to train k and the length scale simultaneously. So that's sort of something which I'm still working on and haven't really gotten a great solution to yet. Just quickly to talk about this last point which I'm working on. Another downside of this is that as the number of sensors increase, the classification becomes more difficult. And in particular, you end up needing significantly more training data. So this is sometimes called the curse of dimensionality in machine learning, where it makes it, as you grow the number of sensors, it makes it exponentially less likely to have a point close in the training set. So you can imagine that if we only have one sensor and 5 points, they are all very close to each other. But as soon as we add a second sensor, the distance between these training points tends to increase a lot. And we could very easily miss classified points that happen to fall between them. And really what we would have to do there is expand the length scales larger than we may like. So what I was thinking here is sort of a semi-correlated approach. And this sort of ties into John's idea of using time as sort of the core signal that you're looking at. So the idea here is that you would just have a few baseline signals, for example, time or some other signal that tells you the state of the process. And then you basically just correlate all the other sensors only to those time or state signals. So you'd individually find the squared distance in a space just comprised of those individual sensors and the state signals. So that would basically tell you how unusual is this individual signal given your point in time or the current state. And then you could sort of sum all of these individual squared distances to get a metric across all of the sensors. So it's not fully univariate and it's not fully correlated, but it can help reduce the curse of dimensionality when you have large numbers of sensors. So essentially, the univariate case would be drawing bounds across this entire distance because you don't correlate it with time. But if you take the semi-correlated approach, it would basically just draw bounds around what is acceptable for this point in time for each of the sensors. So sort of in conclusion, I think that Parzen window classifiers are a simple and effective method of detecting outliers in a variety of different manufacturing processes. I think that a binary kernel can help mitigate false positives, especially because in these cycles, there tend to be very infrequent events that we don't want to classify as anomalous. Also, practically training these, we can use one class cross-validation with only known good data, and that ties into the fact that we will not have examples of faults beforehand. And this amounts to selecting the length scales for the kernel that we've chosen. Also, regardless of which model you end up choosing, I think the concept drift is very common in manufacturing settings and something that you're likely going to have to account for. And here we can choose to account for that by using our floating data set. Finally, choosing acceptable false positive rates in the cross-validation training can help improve model performance by not overfitting to specific examples of sort of borderline cases or potential anomalies in our training data. So any comments, questions, or suggestions?